Sorry, hold on. I'm totally confused. Hello, hello. Hello, 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 Lizzie. Hello, Eric. Hello. Well, and hi, May. Hi, Lizzie times two. Oh, and happy birthday, post birthday. Hey, she's still standing. 2 days after she turned 20, she's like, oh, not even blacked out in a ditch somewhere. That's excellent. Well played. Um, I shouldn't make jokes like that. Good afternoon, Alea. And I said, okay. And right, happy belated. Okay. Good afternoon, Alea. Okay. Oh, and hello, Newell. I think I missed. And okay. Okay. Class is getting smaller and smaller, isn't it? Interesting. This is what maybe. All right. So we're going to get started. Okay, there's logistics to do. I'm getting sad because I'm not going to see you much anymore, you guys. I'm getting sad because I'm not going to see you, and you're getting anxious or upset because you still don't have sort of grading information that you deserve and need. And that is true, and I understand it. Here's a story. Some of you still have not gotten exams back from me. That sounds like a criticism of you. That's a criticism of me. Some of you have, some of you have not. I think all of you have gotten back. If you did the 14-point thing, then I think you've gotten it back. If you did it a little bit late, then I took off, then I didn't give a full 14 points, or if you were missing a final answer, then I didn't give a full. But basically, if you did it at all, you certainly got at least 10 points. And let me remind you that even if you have not gotten your exam back yet, which I apologize, then remember the points that you got on this thing that you just got back, they go directly onto your exam score. Please don't forget that. So like when you get your exam score back, if it's like a 74, then you literally add these 12 or these 14 or whatever points that, and then it's an 86 or whatever, just so you know. Also, we have 2 classes left. I mean, including today. We have today and then we have Monday. I want to try to tie together all this material or show you the point of the course in the next 2 days. It's not going to be a lot of math. It's going to be like a concept or pictures that I'm trying to put together for you. And then what's going to happen, excuse me, and I'll put this in Google Classroom. And those of you who are here right now and still standing and still surviving and haven't given up have my praise and also have a huge advantage over anybody who's not still standing. Like, so please like follow this along what I'm about to say. I will try to put it in Google Classroom, but here's the deal. I'm going to try to put together the material a little bit more today. I'm going to finish discussing the material Monday. And Monday, I will give you a specific sense of the one short document that will serve as our final exam. I will talk you through it on Monday. I might post something in advance, but probably not. I will talk you through it Monday of what I'm going to post Wednesday night, and it'll be a short thing that gives you an opportunity to put this material a bit together. It won't be as elaborate as the midterm. It won't be as long. It won't be as mathematically intricate as the midterm. It'll be posted Wednesday night, and you'll have till the following Monday night to submit it. In other words, you'll have pretty much the whole final exam period to turn it around and submit it back to me. It'll involve a little drawing, a little bit of English, a little bit of math, and it'll be like a couple of pages, not like 6 pages. It'll be like a couple of pages. It will be a last opportunity to help a grade that should already hopefully be a better grade than you think. What I mean by that is this. I know some of you still haven't gotten back midterm scores. So a couple of things about that. If it turns out that you did well on the midterm, better than you think, especially once the 12 points or the 14 points, or whatever, are added, if it turns out that you have a good score in the midterm, like it looks like you're getting an A in the class or whatever like that, then the final exam will not count as much. And it probably won't hurt your grade. Well, it won't count as much. If it turns out that your midterm was like worse than you thought, or worse than I expected, or somehow put you in a slightly dangerous zone, then a couple of things. Then the final will count more for you. I mean, if you, assuming you do better on the final, then I'll count it more. In other words, I'm going to more heavily count whichever one you do better on. That I'm saying that's a promise. Whichever one you do better on, I'm going to count more heavily. So we're both, you and I are looking for you to end up earning a good grade in this class. Like, and there's more than one way to earn a good grade in this class. For some of you, it's by the fact that you've done so many game turns and so many, handed in so many things that you got so many points from that super helped your grade. Some of you will pull it out at the last minute on the final. Some of you rock the midterm and don't even just know that yet. There's more than one way to get a really good grade in the final thing. And we're, both you and I are looking for that way. Like, essentially, you're being graded in this class on your best, not on your middle, not on your worst, but just like if you have found a way to do good work at some point in this semester in a way that counts, whether it's through the homework or through the midterm or through the final, then that's what's going to identify you to me. And let me put the flip side of this whole thing around again. And I'm saying all this partly so to be clear, partly so we can wrap up the semester, but also because I know that the fact that there's still information outstanding for some of you can only cause anxiety and nervousness for some of you. I totally get that if you don't know what's going on, like exactly with your grade right now, then that's every good reason to be nervous. And what I'm here to tell you again is the one thing I know, and I know you know, is that I mean, let me back up for a second. I want everybody to have good grades. Some people won't. I mean, you have to earn a good grade to have a good grade. There will be some people every semester in every section who do little enough or work counterproductively enough that they don't end up doing well. And that's the way it is. But what you and I, anybody who's listening right now, anybody who's here right now of you and I both know that. Sorry, let me turn on focus. Sorry, my thing is going off. Sorry. I only learned about focus, whatever it's called, do not disturb, like a month ago. It's so sad. Okay. What I know, I want you to know that I know. Like, a bad grade is bad. Nobody likes a bad grade, but some people know sometimes when they didn't earn a good grade, and that's just the way it is, and there's no one else to blame. But that's one thing. We both know that what nobody wants is to suddenly be surprised by a really bad grade situation when they didn't expect it and when it's too late to do anything about it. I want to be clear that I know that's a nightmare, and it's like not a fair situation to be in. And it might be the situation that some of you might be worried about right now. You might be thinking, well, he keeps talking like it's all going to be fine. But like, since I don't know what I got on my midterm yet, what if it turns out all of a sudden, like when it's too late, that I really did bomb this class? Like, what if I already know in my heart that I beefed that midterm and he doesn't even know it yet? What I'm here to say is this to all of you, or to the 6 of you who are listening. I'm here to say, first, over this weekend, when I start gathering things together and stuff, and when hopefully you will have already gotten your midterm back, if I suspect, well, here's what I want you all to get A's. I have no problem with you all getting A's. I don't think realistically everybody is going to get an A, but I certainly have no problem if everybody does. I think people can live with B's, especially if they know that they didn't do A work. But where I cut it off in my mind is if I'm looking at your situation this weekend or whatever, if I think, uh-oh, this person doesn't know it, or we haven't discussed it, but it looks like this person, whoever you are, is actually going to end up with something in the C range, or God forbid lower. If I see that it looks like we're heading to C town, I will personally reach out to you and say, wait, before we do this final, before we totally close the semester, things are looking ugly to me. I don't know what they look like to you. Like, is there something we can do to rectify the situation? Like, are there still some homeworks that you could still turn in, or some game turns, or da-da-da? If I think you're sailing for a C or lower, like something in the C range or lower, I will reach out to you. Similarly, if you are personally concerned this weekend, if you're like, yeah, I still am not buying this, like I'm still totally nervous, and then you can reach out to me, and I will sit and look at the situation with you. And if we both think, oh yeah, no, this is not looking good, we'll see what we can do about it. Okay. What I'm just trying to tell all of you is I think it could be conceivable that one of you or some of you could end up with something in the B range. And I don't know if you're expecting that or, I mean, I'm not looking for that, but that might happen. And if it happens because of what turned out happening on the midterm and the final, then okay. And if you're really worried about that, you can reach out to me. But I'm telling you that if it's anything lower than the B, I'm going to reach out to you before it's too late. That's what I'm trying to say. Okay. So if you don't hear from me, as we're going into this weekend or, into the final of next week, I want you to at least understand, but you're still missing information. I want you to at least understand you're not suddenly going to discover a C on your transcript that you had no warning of. It's not going to happen. Okay. If I think something that's not going to happen, then I'm going to warn you and we'll talk. I can't, that's the best thing I could do to say to try to, and again, you might be thinking, well, B is not good enough. Like I'm an A person. Okay, well that may be, but then let's talk. Like reach out to me if you're still concerned, and I will listen. Like we'll sit down and look at the situation. But I'm telling you, that's where my head is. That if I think it's actually C or lower, I will reach out to you. If you don't hear from me, that means I think it's going to work out at least, higher than that. And again, I think a lot of you are going to be in the A range. I'm not, but okay. I can't. So again, to be clear or to be concrete, Tuesday, one last thing will be posted. There will be one last opportunity to affect your grade. Yes, it's technically the final exam. It will be designed to not be hugely stressful to you or to me. It will be designed to help you if you need the help in your grade, given what might have happened on the midterm. Okay, someone's here. Sorry, hold on. And it'll be due back. It will be due back the following Monday, Monday the 24th. Does that make sense? Yeah, I think that's Monday the 24th, but I'll post this in Google Classroom. But that's just so you know how the semester is going to shut down. And then last thing before can I just get a quick thumbs up if you're still hearing me, if this makes vague sense. I mean, it may not be happy information, but this makes sense. Thank you, Alea. I appreciate it. Thank you, Lizzie. I told you that. Thank you. Thank you, Elizabeth. Thank you, Noel. Okay. And Eric and May, you guys are good. I mean, it's a small, yeah, cool. Okay. Thank you. I mean, did I just say May? That is what I meant to say. Yeah. Okay. Sorry. And Eric, you're Eric, not trying to single anybody out, but is Eric still here? Okay. Well, all right. So we're going to go on in a second. There's one. Oh, but one other thing too, before I forget, because again, obviously some of why I'm saying all this is I do feel guilty. And I feel a little bit, I'm not worried for you, but I'm worried about the fact that you might be worried and it would be because of me. So I just also want to make clear that some of you I've had now for 2 semesters. Some of you have had for 1, but I feel like I've gotten to know you remarkably well, given that it's all electronic and it's all, wait, whoa. I don't know if that was a statement. Wait, that was an interesting little Bitmoji flash there. Emoji. Anyway, okay, cool, Elizabeth. Some of you I feel like I've gotten to know surprisingly well, given that this is all electronic and it's all crazy times and all that. And I'm saying that to say that I actually am going to be sad when this class is over. I wish there was a Physics 3. We used to have one, and maybe someday we will again. But even if there's no Physics 3 or whatever, and for some of you might be like, no, thanks. I said, oh, okay, no problem. Even if you're like, yeah, enough is enough, I'm perfectly happy to I just want to make it clear that as you progress in life from this stage on, with graduate school applications, job applications, summer program applications, honors applications, lab tech, PRISM, tutoring, whatever, please do know that I think very highly of you as a group. And I think very highly of you as a group, and I feel like I do know you to a surprising degree, and I can say very specific things about many of you in very specific terms, which not everybody can these days in COVID, if you know what I mean. It's harder to get to know people these days, but I feel like you guys have made yourself known to me. So if there's any way I can help any of you after this course is over with letters of recommendation, support, please do feel free to come to me, and I do take that stuff seriously. And it usually does work out. And I think you do deserve that. And last thing, again, just because it's just that time of the year and it's that time of everything, and it's come up in the other 2 classes. Let me also say, well, maybe I should save the speech for Monday, but just please remember, I know you're science majors. Even those of you who are e-permits or whatever, most of you in this room right here are forensic science majors, but it's a hard major. I've said it 100 times, but I just want you to know that I know that it is hard, like super hard, the major you're in. And often I don't make it any easier. Like I tend to make it harder by the stupid things that I accidentally do. I hope I don't intentionally make it hard, but I don't make your life any easier. Your life is hard. And I want you to know that I know that, and I'm impressed by it. And there's some still hard stuff to come, like instrumental and PChem and biochem. And I see people registering for the courses and all that kind of stuff. I know some hard stuff is to come, but let me tell you right now that you've passed. If you're here and you're getting through physics 2, you're over the hump. It doesn't get easier. I'm not saying that. But if you've gotten this far, you have proven that you can do the rest. And I want you to remember, when each and every one of you has at some point, some moment in the middle of biochem or peak or taking 3, look, there is something to be scared of in some of those courses. And we could talk about that in private too. They're not a joke, those courses. And if you're taking 2 of them or 3 of them at the same time, as many of you do, that is intense. That my hand is off to you already. I understand if you're scared. People, and I'm here, I'm not trying to make you more scared, but I'm here to say a couple of, first of all, when it comes to PChem in particular, save your notes from the first half of this class. I'm not tooting my own horn. A lot of the stuff in this class doesn't help you anywhere else in life. But if any of this stuff in this class does help you anywhere, it's the first half of this course helps with PChem. But that's what people come back and tell me. Just save your just save your notes. But and of course, I'd be delighted to help you with PChem if you come to me with questions. But really, what I'm here to say, and maybe I've said this before, but I really mean it, and it's this time of year, and you don't get a chance to hear this all the time. Please remember that almost no one ever gets through this program without at least a moment of, oh my God, I don't know if I can make it any further. Oh my God, I don't know if I belong here. Oh my God, right, okay, cool, thank you. No, for real, everybody has this moment where they're like, wait, whoa, what am I doing? Are you kidding me? PChem and instrumental at the same time? Like, well, I have no idea what's going, or whatever it is. Everybody in this program has at least one moment where they suddenly have a crisis and they suddenly do all this soul searching and they're like, I literally don't know if I've totally picked the wrong course for my life. And I really don't know if already I'm on the wrong. Okay, so some people have it more than once. Here's the deal. Like the most cocky, even the most cocky people, even if they don't think that, what they privately think is, I do belong here, but I don't know if all this work is worth it. I'm telling you, even if they don't even the people that seem the most cocky, and they might seem the most cocky to you when you're nervous, but on the professor side, we can see, okay, everybody has a moment where they're not sure if it's worth going on in this program, because this program is super hard. And when I say the program is super hard, I want to remind you, even if I've bored you with this before, I want to remind you, I went to undergrad at a ritzy, private, expensive school and did physics there and philosophy. And I went to graduate school twice, one time at a CUNY school, at City College. Okay. So I've had the ritzy, private, like jjP experience, whatever experience. And I've had the public, big urban experience. I mean, particularly the CUNY experience. Let me tell you, both of those kind of experiences are hard in 2 completely different ways. They are hard in 2 completely different ways. But your program that you're in, you guys, this undergraduate forensic science or CMB or tox major, let me tell you from life experience, your program is hard in both ways at the same time. Your program is both like a classic liberal arts, you must know all the classic lab sciences and all the background and the fundamentals as though you're just going to go on and be an aristocratic intellectual. And your program is like, we are training you to have all the skills that you need to actually function in the practical world and get a real job in the practical world and like actually be able to serve the community and get a salary, right? Both are hard in 2 totally different ways, and both are totally different. Your program does both. That is freaking hard. I don't know if I can make it through. I mean, I do think I now could because I know some, but like your program takes all the things that's hard about like whatever Cornell and all, which is not where I went, but and all the things that's hard about CUNY and puts them together. It's very hard, your program. You should be commended. If you have gotten this far already, then you have what it takes. People around you will look like they have something that you don't, when you're freaking out inside, but don't ever make the mistake, which you will every day, of comparing your insides to other people's outsides. Think about that. And that's what we do all the time. We compare our insides to other people's outsides, and don't fall for the trap. If you've gotten this far, if you're a week before the final in Physics 204, you've gotten over the humps. You're the people that do belong here. And when you have your crisis, when you start wondering whether you belong here or not, I want you to remember my voice or someone's voice telling you that moment of crisis does not mean you don't belong here. It means welcome to the club. That's what it means to be part of these rigorous programs. And the reason this program is so meaningful, and the reason your degree matters once you get it and will get you into graduate school and will get you a job, is because not everybody who starts finishes. That's what makes it legitimate. Same with this class. You might think, is he just saying that he's going to give everybody an A? I'm not saying I'm going to give everybody an A. I'm saying if you're listening to me right now, if you've come this far and you're still in the Zoom room at this point in the semester, oh yeah, it's very likely you're getting an A, because you're those cream that's left over having risen to the top of the milk. The reason a lot of you can get A's is because a lot of you won't. And those are the people that aren't even here right now or even hearing me. It's not right. And same thing with the program. If you are left standing at the end, you've done something valuable, because it's not automatic. It's not a gift. Some people can't do it and don't do it. And the difference between you people who will make it to the end and the people that don't is simply that when you have the moment of crisis and you say, I don't know if I belong here, just tell yourself, well, nobody knows whether they belong here. I might as well just take a shot and assume that I do. I'll just do the stuff that supposedly people do if they supposedly do belong here. And I'll just keep going to the end, and I'll find out at the end if I belong. And guess what? You'll get to the end and you'll find out you belong. Like, seriously, the trick to getting the degree is finishing, and the trick to finishing is not stopping. And that's all that's what separates the people that do it from the people that don't. It's not that the people that do it never ask the question. Everybody asks the question. Okay, really. So you guys belong here, and it's going to get hard before it gets easy, but you've passed the barrier of entry. You are the people that will do this, and it will be worth it. And the rest of the world will know it. That's all. Okay, that's it. So please, let me help with letters of recommendation stuff when we get to that point. That's the other thing I'm trying to say. Blah, blah, blah. Okay. All right, I'm looking at chat. So back to the final thing of the course. Okay. Okay, here's the summary. Here's the last question we have to answer in the course. And again, this is going to be more about pictures and words really than math equations for the next couple of days, for good or for bad. Okay, I'm going to try to show you why you did all this math and stuff. So the last question, what it says here on the board is, what about changes in the E field? Someone's here. Sorry. Okay, it says, what about changes in the E field? If the E field is information, how do updates to that information, updated information, work? Question mark. What happens to the field lines? Okay, this is our final question of the class. And it may even sound like a very obscure, or it may sound like a small or uninteresting question. But it is the question. It sort of ultimately, if we can answer this question, we will have put together the whole course. So I want to, so we're basically trying to ask ourselves now, when new information or changes in information in some point in space occur, what happens to the whole picture of field lines throughout space such that some other point in space can receive this new information? That's what I'm really asking here. That's what I'm asking here. When I say information, what I mean is when I say information describing some point in space, I mean the size and directions describing whatever it is that's located at that point in space. So I'm saying, like, how over at this point in space here, do we know that there's a 2 Coulomb point source located over there in space? Like, how do we know what is at a particular location, how big it is, and where that location is? Somehow, whatever is over here seems to be known by any and all points in space over there. It seems to be known, again, why? Because it seems to be the case that when there is a proton over here, if I place an electron somewhere over here, it seems to be pulled toward that proton, and it seems to be pulled toward that proton with an amount of newtons that seems directly determined by or directly dependent on exactly how big that proton is and exactly how much space is between the proton and electron. In other words, again, the driving assumption behind this whole field discussion is that it seems to be true that whatever is located over, when things are located over here in one point in space, it seems to be the case that that data is accessible to any and all other points in space. And so when we put objects at other points in space, they respond. So this information that is everywhere in space, we call a field. I want to know whenever we change that information, we call it a field. The field is represented by field lines. What I ultimately want to know is what happens to the field lines when we change the information. That's where I'm going with this. Let me pause. I'm going to switch screens here and show you some pictures that we were going to look at Monday, but then we got involved in this other sort of interesting related discussion of black holes and stuff. I'm going to switch screens. I want to show you some pictures of field lines. Okay. 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 So on the screen, you can see, right. All right. These are a couple of representative example pictures of field line diagrams. I'm actually trying to remember exactly. I'm trying to remember exactly how far we got on Monday. Monday, I showed you a picture. Well, I'm going to ask you right now. Monday, I showed you guys pictures of vector field diagrams, like pictures of like little arrows coming out. Did I show you any pictures at all of field lines on Monday, or did we stop at the or let me back up for a second. I did show you picture of, I showed you vector field pictures, right? Wait, I'm looking at the chat. No. Okay. Can I confirm? But I did show you vectors, yes? Like, did I? Well, okay, all right, okay. Actually, that's a good enough answer. Thank you, Elizabeth. And I totally trust. Oh wait. Oh, I showed ones that look like oh, that looked like A. Oh, that looked like A. Okay, great. Lizzie, got it. Okay. We saw, okay, good. Okay. Very helpful. Thank you. Good. Oh, that's very, see, this is what I mean. To all of you. See, your class participation is so great. Some of you, and it really makes a difference. Right, going into Q and out from Q. Perfect. All right, now we're on the same page. That all of you, both of you, thank you. Maybe if I have a daughter, I'm totally naming her Elizabeth, and I'll use a Z and an S. That's what I'll do. Well, but she'll be named Elizabeth May Jiaowei Stephanie Newell. Okay. All right, just kidding. Okay. All right. So on Monday, like, okay, this is what I'm trying to say. Monday, I showed you these pictures that had vectors. And the whole idea about that is, again, a field, like field is this abstract idea that we're ending the semester on. I'm trying to jump in every possible way. I'm trying to drum in with you guys, like what a field is. And a field is information, right? Like if there's nothing in space at all, if there's nothing in space, then space is empty. Space is blank. Space is the same everywhere. The idea, according to physics, though, is the minute we put one object in space, right? If I put one proton into space or into the space of a laboratory or whatever, if I originally had this blank, empty, literal space, as in outer space, as in nothingness, as in a vacuum, right? If I put in one proton into that vacuum, well, now the vacuum's not empty anymore. Now there's a proton in it. Now there's like a little unit a little unit point source of charge. Fine, like we all understand, a thingy thing is now in the space. But what physics says is, okay, but something else happens. The minute that you put a proton into space, it's not just the proton itself that you put into space. Immediately upon, as soon as you put the proton in space, what also happens is the vital stats describing the proton get deposited everywhere in space. Like literally how big the proton is and where it is gets deposited everywhere in space, such that if any electron ever, if a second object ever were to come along and get deposited in the space, now what we're saying is the minute a second object gets deposited in space, it's not being deposited, it's being deposited in a space that's empty of any objects, but it's being deposited in a space that is full of information. That the minute we put an electron down somewhere in the space, it's right there, wherever it is, somehow is the data describing the original proton. And that data, I don't know how, like, I'm not saying there's literally a piece of paper there. And I'm not saying there's literally like a styrofoam numeral or something there, but I'm saying somehow the information in some immaterial way is there so that the electron will register that information and know, oh, there's a proton over there, it's 3 miles away, and the electron will start being attracted in that particular direction with that amount of newtons of intensity, of force, okay? Now, what I'm saying is that something like that has to be true because the world seems to work the way the world works seems to indicate that information is there to be retrieved by the second object the minute the second object is placed anywhere in space. Now, I don't know exactly how that information is sitting in space. Like it's not sitting in the form of a styrofoam numeral. It's not sitting in the form of a piece of paper, but somehow it's sitting there. So what we might have pictured that a bunch of numbers were everywhere in space somehow, but that's not a good enough picture because it's not just amounts of force that are sitting ready to be incorporated and used. It's also direction that's everywhere in space, sitting there being ready to use. So we make this picture, the pictures that I showed you Monday, say, okay, here's a way we could think about it. We're not literally saying it's like literally true, but here's a way we could think about it. We could think of a field as like a function, like an input-output thing, where the input is any given point in space, and the output is an arrow. Like, so the pictures I was showing you Monday kind of were good, reasonable, helpful models of how we might understand this field of information to be. We would understand it as like, you pick a point out, like if there's a proton right here in the center of my lab, you pick some random location up there, and there's a little arrow pointing away from the proton, and the size of the arrow indicates how hard you would be pushed, and the direction of the arrow indicates like which way you would be pushed due to that proton, right? So we have these like pictures of arrows of vectors was the ones I was doing for you Monday. But it turns out, okay, that picture is perfectly good. There's nothing like wrong with it, but it becomes very cumbersome and complicated to draw for any situation that's even slightly more complicated than just one point. Like drawing all the arrows becomes a big hardship. It's not wrong, but it becomes incredibly inconvenient. So we come up with this method instead that's based on that method. We come up with this method of drawing and representing and visualizing and computing fields called field lines. And if you look now, so if you look at the picture to the left, there's two pictures on the share screen right here. If you look to the one to the left, that's my new picture. Oh, sorry. Wait, sorry. Wait, sorry, I didn't see Xiaowei's thing before. B is appropriate. I'm just not discussing it yet. I'm going to explain B in a minute. Just hang on. Right now, I'm saying like B is of a different situation. I'm going to explain B in a second. But right now, what I'm saying is with picture A, with this picture here, this is the field line representation of the positive point source. Like this is the new way of drawing what 2 days ago we drew with a bunch of decreasingly short arrows. In today's picture, we took all the arrows that were pointing in the same direction and along the same radial line. We just connected them up and we made one big arrow, okay, for each set of those. And so these arrows are no longer vectors. There's a lot fewer arrows to draw. And what you start seeing in the picture to the right, I'm going to start talking about the picture to the right, but this method of drawing longer lines rather than individual arrows allows us to start capturing and representing what's going on in even complicated situations, like two charges next to each other, which is the second picture to the right, something that would be very hard to draw with a bunch of individual arrows. Let me tell you how this picture works. In fact, I'm going to say, please write, I'm going to give you some rules. I'm looking at the time. I'm going to give you the rules of drawing these pictures. Not that you have to draw a million of them yourself, but I'm going to give you the rules of drawing them so that you really know how to read them and understand them. I mean, the rules for drawing are the same as the rules for reading them. So please somehow write what I'm about to say. I want to keep the screen up, so I can't really type these out for you. But here we go. Rule number one. Well, really, sorry. Rule number zero. Rule number zero, we pick a scaling factor such that each coulomb of source charge, each 1 coulomb of source charge will produce a certain number of lines. Okay, I mean, you don't have to write the exact words I'm saying, but I'll say it again. Rule number zero is we pick a scaling factor that connects coulombs of source charge to number of field lines. What do I mean by that? I mean, like if you look at this picture to the left, you see that there are 8 lines coming out of that dot. Now, the eight lines don't mean that there's only field at each of those locations where the lines are. Like we said on Monday, those lines are just enough lines drawn to show a pattern. The idea is that the lines are actually everywhere. And we've drawn just enough to show the basic arrangement of the lines. We assume that pattern would continue like that everywhere between the lines. So we just picked a certain number of lines to draw. In this case, we picked 8, right? Let's assume for a minute that positive source point of charge is a 1 coulomb charge. Like, I don't know what it is. I mean, it doesn't say in this Google site, but let's say that's a 1 coulomb of source charge. If I drew 8 lines coming out of it, that means I'm going to stay consistent with that scale for the rest of my whole diagram. It means anywhere. It means, for example, that say everything you were looking at here was one big situation. If you look at the picture to the right, assuming this is all part of the same scaling factor, you look at the picture to the right, you see that positive charge, that plus, that blue plus thing, that has like, I don't know, 24 lines coming out of it or something. I can't even count that fast. 1, 2, 3, 4, 5, 6, 7, 8. or like 32 lines or something coming out of it. That means if this whole thing is drawn consistently into scale, if this is all part of one system, then I can assume that that charge, that blue charge, that positive charge at the left half of diagram B, I can assume that that is like a 4 Coulomb charge, right? And the one to my left is a 1 Coulomb charge. In other words, I pick a scaling factor. So the bigger the some charge is, the more lines come out of it. And I just stay, and I pick some scaling factor that works, that gives me a reasonable number of lines, enough to see a pattern. And then from then on, like once I pick the scaling pattern, then every time I have a source charge and I've started to make lines come out of it, I'm going to just draw them in a symmetric way. Like I'm going to arrange them nicely coming out, but I'm going to stay consistent with that scaling factor that for each 1 Coulomb of charge, I'm drawing a certain number of lines. Okay, that's rule number 0. Then rule number 1 is any line, any field line that ever starts will start at a positive, just like you see in these pictures here. Okay, and so any line that ever starts will start at a positive. Otherwise, like semicolon, otherwise the line will come in from infinity. Okay, any field line that starts will start at a positive. If not, the field line comes in from infinity. I'll explain that more in a moment, but let me give you this. That was rule number 1. Any field line that starts at a positive, otherwise it comes in from infinity. Rule number 2 is any field line that ends will end at a negative, otherwise it will go off to infinity. Okay, so let me stop for a second and explain what I mean by those 2 rules. Like in a way they're obvious, but in a way they're not. The simple way, let me look at the chat. I'm sorry, wait. Yes. Yes, what Jiawei, cool. Wait a second. There's great stuff happening in the chat. Okay, first of all, Jiawei's question, yes, good question, Jiawei, and yes, if I understand correctly, like lines that start have to start from positive charges. Oh, thank you so much. Thank you. That's correct. And if they end, they'll end at negative. And I'm going to elaborate on that in a moment, but yes, that's correct. Then now, Elizabeth, that's a great question. I think I understand what Elizabeth's asking. I'm going to say more about Elizabeth. So Elizabeth's asking, assuming the source is positive. That's a really important question. I want to say more about it in a minute, but and I say this with total respect for the question. I actually think the answer is, if I'm understanding it right, I think the answer is no. Like sources. Well, and maybe I don't know what she's saying that in response to, but a source, remember from Monday, and I remember this was Elizabeth's big point, definitely on Monday, or one of Elizabeth's big points. Like the test charge, we're always assuming to be positive. We're assuming that these lines say what will happen to a positive receiver of force. Like all of these lines tell us what would happen if we placed some hypothetical imaginary hypothetical positive little charge somewhere in the space. So that assumption is correct. But if source means the thing that's causing the field, if source means the thing that's creating the push or the pull, then a source could be positive or negative, or like some combination of the 2, as in this diagram B is the field due to a source. Like the source is that pair of charges, that pair of equal and opposite charges. Like both of them are considered a source here in that they are creating the field. Like granted, the lines are going from one to the other, and I'm going to discuss that more in a minute. But what I'm really trying to say, this is a really great question if I'm interpreting it right. Like if you just have one positive charge sitting in space, as in diagram A, then it makes a field that looks like that, like diagram A. If you put a negative next to it, then together they make something called an electric dipole, right? They're like a hydrogen atom, like a one proton and one electron. Together, they're creating a field. They're influencing the rest of space in a very specific way that's very different from if you just had one positive or if you just had one negative. So together, they are a source of field. I do understand that the lines are going from one to the other, and I will address that further in a moment. But what I'm saying right now is when I use the word source, I mean anything that can create a field, anything that's going to push or pull on other things that we would then call the tests. So sources can be positive or negative. And it is also a little, so wait, I'm going to go on. Well, I don't know if I'm going to go on a little bit more with this, and then we'll see if that answered Elizabeth's thing or not. But I know why this is confusing, or I mean, I think I know why. Because going back to the rules now, let me go back to the rules for a second, and then hopefully this will address this further. In the rule number 1 and rule number 2, I'm saying lines that ever start must start on positive, and lines that ever end must end on negative. So, like, why am I phrasing in this weird way? Like, that almost just sounds, I mean, that used to always confuse me. It sounds like, okay, so you're saying lines go from positive to negative, right? End of story, verbatim. No, what I'm saying is, what I'm really saying with those two rules is lines can either come from a positive, as they all certainly, as many of them seem to be doing in B, well, in the left part of B, of diagram B, or they can come in from infinity. As you see all of those lines, on the right side of diagram B, you notice all of those lines, they sort of look like vectors, kind of, because they're arrows, right? And they do have arrowheads on them, but they seem to have these tails, right? I mean, the lines seem to end on the page, like at the top of the page, there's just this, the line cuts off. What I'm trying to say in rules 1 and 2 is wherever those lines are stopping like that, like they just seem like there's just tails there, if those tails are not on a definitive positive charge, then those tails are not the end of the line. Those tails are just where the page got cut off. What we're supposed to believe about in all field line pictures, in other words, is if you ever see a tail, if you ever see a line end, but it's not ending on a negative, it's not ending on a source of some kind, then that means you're supposed to understand that it's just coming in from forever. The lines go on forever. In other words, what I'm really trying to say is these lines do not ever stop or start in the middle of blank space, in the middle of some blank space on the page. They can only actually stop, like have a tip on a negative charge, and they can only actually start, like have a tail on a positive charge if they ever look like they're like. So similarly on the left side of diagram B, or if you look at all of those tips in diagram A, it kind of, they're very deliberately being drawn. Notice, like, this is a good way to put it. Notice the tips aren't even drawn at the end of the line. They're drawn in the middle. They're done that way on purpose to really emphasize to you, these things are not vectors. They don't have length. None of these lines has a finite length unless it literally goes from a positive to a negative. If it's not hitting a negative or hitting a positive, then we're supposed to understand that they just go on forever like that. They don't have a specific length the way vector arrows do. Okay. So, let me see the chat. So that's really what I'm trying to say by rules number 1 and 2 is that field lines do not stop or start anywhere in space. They come from infinity, they go to infinity, and the only way they ever stop or start is they get started by a positive and they get ended by a negative. And then last thing, I'm going to look in the chat, and this might have to do with what's in the chat, or this might have to do with Elizabeth's thing, but therefore, it's true that some people will call positive charges sources because the lines come out of the positive charges, and some people will call the negative charges sinks. This might be what Elizabeth is getting at. Like, some people will call the positive charges sources because the lines come out of them, and some people will call the negative charges sinks because the lines go to them. But what I'm saying, and that's not wrong. I'm not saying that's wrong. I mean, that, and if that language works for you, like good. I mean, it is accurate that lines go from positive to negative if they're going from anywhere to anywhere. But what I'm saying is in the language of fields and the language of physics, both the source and the sinks ultimately are a source of a kind in the sense that both of them are what's causing field. Like last way of putting it, and then I'll look in the chat. What I'm saying is even if you had a negative just sitting on the table, even if you have an electron sitting by itself on the table, then you got a bunch of lines pointing in to that negative, like we said on Monday, right? Like a negative doesn't need a positive in order to create a field. A negative can create a field by itself. It's just that it's an inward pointing, pulling field rather than an outward pushing field. Okay. So that's the sense in which I mean both negatives and positives are sources in the sense that they both create field. But yes, technically, but if you want to be more specific, one of them you could call like a source, and the other is like a sink source. Like I get, and that may be what Elizabeth's getting at. I'll find out, and maybe it's already in the chat. I'm going to look. But hopefully this makes sense sort of so far. Let me look. Oh, there's two things in the chat. All right, let me see. Oh, okay, cool. Okay, so first of all, Elizabeth, I totally appreciate your honesty and your communication. And fair enough if you don't totally, we'll keep going and we'll see, but I totally appreciate how closely listening. And then, wait, so B is not correct. No, but wait, so Xiaowei's question is very good, but B is correct because the lines aren't starting from negative. Wait, so B is correct. I don't know, like lines are allowed to, you're right, lines cannot start at negative, but they're not in B, they're ending at the negative, right? The arrows are pointing from positive to negative. I'm not sure what, maybe Yahweh should say more, but I think B, so what I'm saying is A is the correct picture of the field due to or produced by one point source. B is the picture of a field produced by a dipole, by a equal and opposite pair of charges. Both pictures are trying to tell us, well, I'll go on with the rules. That may help also, but both pictures are trying to tell us what would happen to some test charge of positive 1 coulomb that might land anywhere in the space depicted by either of these pictures. Like picture B is not telling you what the positive is doing to the negative. Picture B is telling you what the two of them together are doing to the surrounding space. I don't know if that helps or not. Oh. Lines start from positive to negative. Central particle could be. Yes. What Jarway said in the chat there is correct. I don't know if that is what, but yes, that's correct. That's good. I guess I'm nervous to say this, but there doesn't necessarily have to be literally a central particle. I mean, there could be two, but yes, yes. All right, so I'll keep looking at the chat. I mean, these are good questions. They're definitely good questions. I'll keep looking at the chat, but let me keep going with these rules though. And hopefully you are writing these rules down. Again, I would write them for you, but I think these pictures are super important. So rule 0 was you pick a scaling factor, number of field lines per each coulomb of source charge. That was rule number 0. Rule number 1 is if lines start, they start at a positive. Otherwise, they come in from infinity. Rule 2 was if lines end, they end at a negative. Otherwise, they go off to infinity. Okay. Rule 4 is rule 4 is I'm just trying to say this in the most concise manner. Sorry. Rule number 4 is in any region on the page, the orientation of the lines represents direction of field, orientation of lines, orientation of arrows, you could say. Orientation of arrows represents direction of field, and density of lines represents magnitude of field at that region of space. So I'm going to say this again. At any region of the page, orientation of arrows represents direction of field, and density of lines represents magnitude of field at that region of space. And if you want to put in the chat, if you want me to say that one more time, I will, or I will in a minute. But let me try to break, but you don't need to say my exact words. I just want you to get the idea. And here's the idea that I'm saying. I'm saying that this whole picture is still, so this was rule 4, by the way. There's still a couple more to come. But this whole picture is meant it's supposed to do the same thing that our vector picture did on Monday. It's supposed to be giving us a way to visualize what the field is doing at every point in space due to something that's creating that field, due to some source charge. When I say the picture is supposed to be helping us visualize what the field is doing everywhere in space, I mean, at any given point in space, we're supposed to be able to read what the magnitude and direction is of the force that's waiting to happen, right? The whole thing that we're talking about here is if we had 1 unit of positive test charge placed somewhere in space, how hard and in what direction would it be pushed or pulled by the source charges, right? The field is how hard and in what direction you'd be pushed or pulled. The field lines are supposed to tell us that. The field lines are supposed to tell us magnitude and direction, just like the vectors told us magnitude and direction. But we got rid of the vectors and we have these field lines instead. Well, just like the vectors, we still have arrowheads. So the arrowheads are still telling us direction. Like we still have that same idea going on, that the way a line is heading, the way it's oriented, that tells you what way you'd be pushed or pulled if you were a unit of positive test charge there. But with the arrow, but we also need to know magnitude. We need to know how strong or weak the field is in a certain region. Well, with the arrows, that was easy, like the vectors on Monday. The longer the arrow, the stronger the field. That was the idea behind those vector arrows. And I mean, maybe it wasn't easy, but I mean, it was somewhat straightforward. The arrows got shorter and shorter as we got farther away from the charge, indicating that field was getting weaker and weaker as we got farther away from the charge. And why does it get weaker and weaker? Because KQ over R squared equals E, because the bigger R is, because R is in the denominator. So the farther away you are, the weaker the whole thing is. Now, I'm saying when we had vectors, when we had individual arrows, the length of the vector indicated the magnitude of the field. We don't have that luxury anymore. The good news is we got rid of all those little arrows, so this is a lot easier to draw and maybe even easier to look at. But now I'm saying from rules 1 and 2 that these lines go on forever, or in the case that they don't, and when they land somewhere, they're landing at a charge. So the length of these arrows doesn't mean anything. We can't infer, they don't have length. So how do we infer from these pictures? I'm not asking you, this is a rhetorical question, but the question is, how can we use these pictures to represent or to read how strong the field is in a particular region? And the answer is density of lines. Like that's what I was saying a minute ago when I read the rule out. By density, I literally mean number of lines per unit area on the page. Like what I'm, and remember, this goes back to really rule 0, the scaling idea. Like notice we have a lot more lines coming out of the positive charge in the left side of part B than we do number of lines coming out of the positive charge in diagram A. What are we saying? And we picked that scaling factor because we think that diagram B has a stronger charge sitting there. Well, stronger charge makes stronger field, right? E equals KQ over R squared. The bigger the charge, the stronger the field. So, and this diagram totally captures that. Like if you just look, there's a huge, dense, crowded, like gathering of lines in the left-hand side of diagram B, much more so than in diagram A. What that indicates is that if I were somewhere nearby, if I were somewhere near the plus sign, the blue charge in diagram B, I'm in a region of much stronger field than I am in diagram A. Even better, let me go a step further, and then I will look in the, oh no, there's nothing. Let me go a step further and say, just look at charge A itself. I mean, excuse me, just look at diagram A itself. Like that's just one simple charge that's supposed to be creating field, one simple point source that's supposed to be creating field. And we're supposed to believe like E equals KQ over R squared. I believe that as I get farther from that charge, the field is supposed to be weaker. Well, how can I tell that? Looking at that picture, like no lines are getting short or anything, but look, the lines are getting less spread, or they're getting more spread out. They're getting less dense as I get farther and farther away from that charge. Like in other words, like really close in the inner circles of diagram A, I'm in a region where the lines are very crowded together per unit area on the page. But if I go far, far out, the lines are spread out. They're far apart. So we can use and similarly, if you go over to diagram B, I'm saying if you use density of lines to represent strength of field, magnitude of field, even in a picture like B, you can tell, or you're supposed to believe, that the field is very, very strong right along the x-axis at a point equidistant between the positive and negative charge, like right in the whole middle of the picture. There's tons of really crowded lines right there. That indicates really strong field. If you were going far away, like way to the top of the picture, to the center of the picture, but way on the top, the lines are now far apart from each other. That's weak field. And again, remember, this whole diagram is supposedly drawn to scale. It helps that it was drawn by a computer. So the lines are not random. They're indicating something. So, and I'm going to keep going. I know we've got 12 minutes. So rule number 4 is, rule number 4 is crucial. It's like how these diagrams work. In vector pictures, length of arrow indicates magnitude of field. But in field line diagrams, as we are now looking at, density of lines per unit area on the page indicates represents magnitude of field. Okay, that was rule number 4. Rule number 5, lines can and often do bend. Like lines can bend or curve, but they cannot cross. Okay, rule number 5 is lines can bend and curve, but they cannot cross. And you see that's what's happening in these pictures, right? They can bend and curve because they're not vectors. They're just lines. They don't have to be straight, and they often won't be straight. But they can't cross. Now, like, when can they bend? Why do they ever bend? You'll see when we get to the end of the rules, they'll bend if they have to bend in order to draw a picture that follows all the other rules. And as long as sometimes they have to bend in order, if a line has to start at positive and it has to end at negative, and it has to follow all the other rules, some of which I haven't finished yet, sometimes it'll have to bend, and that's fine. It doesn't contradict anything. There's no reason it can't, but it can't cross. No lines can cross each other because each one of these lines is supposed to represent the net force per charge that's occurring at a certain point on the page due to the contributing force vectors that came from every bit of source charge creating the field. In other words, this is where all the work that you did for the 14 points comes into play. That whole sheet that you did, even if you didn't fully, perfectly think you understood every single calculation you did, or even if you think some of them are wrong, what you were attempting to do there, you in that sheet, the 14-point sheet, you had two, I mean, it's much like this picture. You had 2 point charges somewhere in the XY plane, and one of them happened to be positive, one happened to be negative. Now, in your case, they were of different sizes. That's fine. But what you were trying to figure out was you were trying to figure out what's the field, what's the magnitude and direction of the field at a particular position in space, the origin. You were trying to figure out the field at the origin due to these 2 source points that you had. In other words, you were trying, and what you did to figure that out is you decided that each one of these point sources created its own little vector, its own little force per unit charge vector that pointed in a certain direction and had a certain length, and you added those vectors together, and you got a third and final vector, like we always do when we add vectors together. You add them together, and what you ended up getting was like the hypotenuse of its own triangle, and your final vector was the vector representing the field at that point. Well, what does that got to do with this diagram? Well, what you did was you calculated one of the points in this diagram. This diagram is trying to simultaneously show us what's happening everywhere due to 2 point sources. You did all those computations just to figure out one of the points. It's a lot of math, as you can see. As you can see, if we want to know anything more than just one point, if we want some sort of sense of the whole arrangement, these pictures become very, very useful. But these pictures are showing what vector sum we would get at each of these. In other words, these curved lines all show what would happen if you took all of the outward vectors from the plus and added them to all of the inward pointing vectors from the minus. These field lines, each one of them is itself representing a vector sum. So what I'm saying is, if in any way we have a contribution from one charge and we have a contribution from the other, they add up and create a final line, just like your 2 vectors in your homework added together to create a new and final vector, and then they went away. They're not part of the field anymore. Same thing here. So what I'm saying here is the only reason any 2 lines would ever cross is because you have a line from one thing intersecting with a line from the other. But then they would add as vectors. And what this diagram is, this is the diagram that we get once we've already done all the addition and all of the crossing lines have been vectorially added together and produce final results. This is the final result. So none of these lines should ever cross. If they cross, it means we're not done. We haven't completed the picture yet. Okay, so rule number 5 was field lines can bend or curve, but they cannot cross. Rule number 6 is that, and we're almost there. There's just 2 more rules, and we're almost done with class 2. Rule number 6. Sorry, just give me an electronic hand if you're still with me and you're getting even if you don't fully understand, if you're getting these rules down, if you're able to actually write these rules down, can you just give me an electronic? Oh, cool. Okay. Thank you, Lizzie. Okay, thank you. That's one. Wait, oh, just tell me, not if you're totally understanding, but just if you're getting these rules down that I'm saying. Is it only one person? Oh my God, am I going to like cry? Raise your hand if you're hearing the rules. Raise your hand if you're hearing me now. Okay, wait. Oh, thank you. Well, thank you, Lizzie. And wait, I think I just saw. Wait, what's that? And thank you, Elizabeth. So is it just the 2 of you? Well, I'll keep going. This is hard stuff. I know. Just everybody, can I get you back in? Raise your hand. Raise your electronic hand if you hear me now. Anybody, everybody. Oh my God, this is bad. Thank you, Alea. Okay, and thank you, Lizzie. I totally see. Thank you, Alea. Was that May? Are you guys? Please, I know we only got 6 minutes. Just hang in there with me. I know this is abstract. Or tell me. Oh, thank you, Elizabeth. I think I almost want to say, tell me what I can do to make this, but I gotta just keep going. Just please, everybody know if you can hear me now at all. You do need these rules. You don't need to understand everything right now, but you need them in life. Well, all right. Anyway. Oh, now I'm going to cry. Okay, so that was rule number 6. Rule number 6, the pattern, the arrangement of lines should get more and more uniform or constant or simple as you get farther and farther away from the source. I'll say that again. The arrangement of lines should get more and more uniform or simple or constant as we look farther and farther away from the source. Okay, put another way, I'm just saying the closer you get to the source, the more complicated the lines should be. As we get farther away in the limit, if we went all the way to infinity, the arrangement of lines should be really, really simple because we're practically in just deep, empty space by the time we get to infinity. Like we're not really, like the closer we get to these things, the thicker, the stronger the field should be, and the thicker the arrangement and the more complicated the arrangement. Okay, so whatever, that was rule number 6, is that the line should get more simple as we get farther and farther away from the source. But finally, rule number 7 is, in general, the arrangement of lines should, this is the most important of all. And we're just about over, whether it makes sense or not, this is the most important of all. Rule number 7. Wait, okay, I'm going to do this again. Raise your electronic hand if you hear me right now. Just if you hear me right now, raise your electronic hand, please. Wow, wait. Okay, slight improvement. Okay, thank you, Noel. Thank you, Alea. Thank you, Lizzie and Elizabeth. Okay, that's a slight. All right, so please, even if you haven't gotten the others, please write this down. Thank you, that's 4 of you. Thank you, and I'm totally horrified for everybody else. But rule number 7 is the arrangement of lines, of field lines. The arrangement of field lines should be as symmetric, as smooth, and as simple as possible while following all above rules. I'll say that one more time. The arrangement of field lines, this is rule number 7. The arrangement of field lines should be as symmetric, as simple, and as smooth as it can possibly be while still obeying all the above rules. Maybe I'll say one more. No, okay, that's so what I'm saying is, I'm going to quickly, I know we have 2 minutes. I'm going to scroll down to some other pictures. I'm going to show you like how, well, that's an okay one, but hold on. All right, like here's 3 more pictures. Okay, these are 3 other arrangements. All the way to the left is the dipole again. Oh, I guess it's 2 new arrangements and 1 old arrangement. All the way to the left is that dipole again. It's a positive charge and it equal but opposite negative charge next to each other. Okay, in the middle is 2 positive charges next to each other, and all the way to the right is a positive charge next to a negative charge. But the assumption there, what you can tell or you can see the difference between all the way to the right and the one, in other words, figure C, the difference between figure C and figure A is that in figure C, it's assumed or that the positive charge is far, far stronger than the negative charge. Like it's like a +5 Coulomb positive charge and maybe a -1 negative charge. That's what that arrangement is. Now, what I'm saying is this: I'm not expecting you to memorize these pictures. I'm not expecting you to draw pictures as elaborate as this. I'm trying to say basically 2 things. I'm saying on the one hand, yeah, these pictures are kind of elaborate. They are kind of richly textured and kind of intricate. And that's kind of interesting given that they're actually the field pictures of comparatively simple arrangements. Like we're just talking about 2 dots of charge here, and we get these really fanciful things, right? And in fact, again, like the picture all the way to the left is a positive and a negative, and the picture all the way to the right is like a strong positive and a weak negative. That doesn't sound like that's that big of it. That's a fairly, they're both simple arrangements and they're both not that dissimilar, but they make this very different field picture. The field picture, as intricate as it is as simple as it can be and still capture all the information what that picture is, since it's 420, I'm going to end with this, but I just want you to see field pictures are always these pictures that are somewhat smooth and symmetric, but somewhat intricate and complicated. Whatever their complications are, indicate the complications of whatever's causing them. Like literally, these pictures are only as asymmetric as the things causing them. The way they tell space, the way they tell this point in space over here, the way this picture tells this point in space where my arrow is over here, what's going on over there is by the lines. The lines are only as asymmetric as this arrangement is. So this point in space can tell what's going on over here because of this pattern of lines. This pattern is the pattern that works for only this arrangement. So I'm just going to leave it at that for today, but field lines are information. They are information that gets conveyed. They're information that you could think of as the difference that makes a difference. Field lines only do weird things over here because there's weird charges over here. Field lines start getting more and more normal over here because there is nothing over there. Field lines are just as asymmetric as whatever it is that's causing them. I'll just leave it at that. You've been very patient, especially some of you. Okay, but you're all being very patient. And I love you all, and I'll miss you all, and I'll see you all. Goodbye. Thank you very much. Thank you in particular, and you. Thank you very much. Thank you. I appreciate it. I'll see you soon. And I'm stopping the recording. And thank you. Yes. Have a nice day, everyone, and happy birthday.
Professor,